talk.
Excellent. So can you all see my main screen, or is it my presenter view?
We can see your your presenter view. Yeah.
Okay, how about now?
Now.
Oh no, go back to the other one.
Okay, sorry. Thank you. All right, so thank you very much to the organizers for putting together this fantastic workshop. I really enjoyed being here yesterday. As Francesca mentioned, I am joining from Houston, where it is still nighttime, so please excuse any incoherent statements that I make. So I was asked to give just an overview of recent progress and next steps in water isotope-enabled modeling. That overview really went over a lot of the talks that have already been given and the posters that have incorporated water isotope-enabled models into our research. And so many of the themes I'll talk about are themes we've already discussed during the meeting. So water isotopes are really valuable in climate research in general because they provide a link between the past, present, and the future. So we often measure water isotopes in our paleoclimate archives, such as ice cores or speleothems. In the present, we have modern observations from both satellite data and our GNIP array, for example. And then we also have water isotope-enabled models, which allow us to incorporate our advanced understanding of changes in the hydrological cycle through time into our projections. So as we'll discuss at length today, we have water tracers for the different isotopic species. And this is important. It's important that we incorporate these common language units into our models, because as many other speakers have discussed, water isotopes have so much to offer from a scientific perspective. I really like this summary figure from Joe Galuski's review paper from 2016 that just shows all the ways in which small scale changes in deep convective systems or in monsoon systems can affect the water isotope ratios in local environments that we measure. And then from a large scale circulation perspective, this figure from Jessica Moorman's paper looking at oxygen isotopes in cave drip water shows the correlation between precipitation delta 18O and regional precipitation as compared to just the local precipitation alone. And this really shows that the water isotopic imprint at the site is giving us a whole tropical Pacific regional signal rather than just a local information. So we can really retrieve information about moisture source, advection, convective history, cloud or rain type, continental moisture recycling. They're incredibly rich data points. And so adding water isotope physics to our GCMs and other scales of models is really a no-brainer. So for many, many years, we've used climate models to assess our physical understanding of the Earth and look at climate change projections. And given that water isotopes are these powerful tools for understanding hydroclimate and circulation, as we just mentioned, they have regularly been added as tracers in GCMs of late and been incorporated into the atmosphere, ocean, and land surface components of our models. And as we'll see today, I hope that I can convince you that water isotopes, could provide key constraints on features of the hydrological cycle and the climate system at large that we still don't perfectly understand, and can help us improve our parameterizations in our models to improve our projections of the future. So first, I wanted to give some historical background. There were many, many pioneering studies in the 60s, 70s, and 80s that have allowed us to build water isotope physics into our climate models. So really pioneering modeling and laboratory experiments. I'm sure we've all cited, those of us who do modeling many times, Majou, Merlevan, Giselle, Craig and Gordon, Stewart, 1975, who wrote this one paper on rain re-evaporation and never showed up again. I don't know what happened to him. And the supersaturation over ice parameterization, these are all based on classic papers that we all use. And I would be remiss if I did not mention the seminal work of Sylvie Dee. I am very enthused that I share a first name with Sylvie, and I remember being in graduate school and figuring out that that lead author was a woman named Sylvie and being very excited. So this is the figure from the original isotope-enabled model from LMD, which was published in 1984 in Nature, which is really incredible because my understanding is computers were not that old at that time. And since then, we've made some advances in water isotope-enabled models. So over the last several decades, we've expanded into many of the different modeling centers. So many of these references are people that are in our workshop today. So, you know, familiar names like David and Gavin and Jung-Eun Lee and Kay and Martin and Camille, we're all here at this workshop. And so I was, you know, lucky to be able to add my name to this list in graduate school with the little model that could, Speedier. And really the past 2 decades have seen major advances, but also expansions in incorporating stable water isotope physics into our atmospheric GCMs. The models we're running today, you know, a lot of these are, you know, 10, 20 years old, are updates of many of these models. So, right, these versions have been updated extensively. Every time we go through a new CMIP, the isotope-enabled model is short behind, and our new versions are adding complexity and accuracy as well as new functionality and facilitating new scientific questions. So for those of you who do isotope-enabled model development, we know this is a tall order, so I just have this sort of funny screenshot from my PhD defense, which was more years ago than I care to admit. But you know, this work can really be a whole PhD's worth of work, and it's a tall order to get the isotope tracers working and debugged and break apart the atmosphere and add new physics components. And so it is a big lift to get isotope physics into our models, and that should be acknowledged because it does take time and a lot of work to get this moving. And yet, despite the fact that it is difficult, expansion has continued. So this is a figure from our US CLIVAR Water Isotope Working Group workshop report. So we had a meeting in 2019 in Boulder, and this is just comparing many of the isotope-enabled models on the market today. And the number of models with isotope tracers is rapidly increasing. And again, this reflects a growing appreciation for their valuable role in evaluating and improving climate model physics, but also now chemistry and biology. And then also their unique contributions to improving our interpretations of paleoclimate records. And I'll talk a little bit more, since this is more my area of expertise, about their critical role in linking observations to models in the paleoclimate realm. We have a hierarchy of models that are available depending on the type of scientific question we're trying to answer. So whether you're trying to do long, fast physics simulations where, you know, with Speedy I can run 1,000 years in 9 days, or you're trying to do very small scale, you know, weather synoptic scale process modeling, there are a hierarchy of models available. So, you know, whether you want the 1980s version of the video game or something closer to the latest version of Grand Theft Auto, you have a hierarchy of models available for what you would like to do. So I wanted to talk about some of the new capabilities and highlight some of the recent work that has been done. And this is where so many of the talks yesterday really covered these applications in great detail, which is amazing to see. So first of all, we've expanded our simulations over both time and spatial scale. And so in time, right, we have modern and future simulations that we've been running for a long time. Most recently, though, we also have last millennium and last 2,000 years simulations. The isotope-enabled version of CESM was recently made public. I know there are many, many last millennium simulations from MPI, for example. And then there are also transient simulations going back to the last glacial maximum with isotopes. I love Climb, iTrace, I'm sure I'm missing many others. And then we also have high resolution modern simulations from our fine scale models. So then in terms of space, right, we have gone from GCMs, but now regional climate models, weather forecasting, cloud resolving models, and large eddy simulations. So again, we really have a hierarchy of complexity and coverage in both time and space. This is the summary table from, again, our water isotope workshop report. I meant to mention this on my first slide, but I'm deliriously tired. But my co-authors are all of the authors of our CLIVAR working group, really. So I'm really representing the full workshop. But this was the table we came up with the most recent versions of these different models that have been published. And again, you can see that they've been developed for different problems and on different spatial scales. Okay, so key opportunities in water isotope-enabled modeling. During this workshop and also at our previous one, we developed several key areas for scientific inquiry that we can uniquely address. So this is just a snapshot of the table of contents of our summary report, and similar themes are emerging at this workshop. So we have progress in developing new models, but also data science tools, which are pressing our water cycle questions forward. Isotope ratios are really a lens by which we can examine the connected hydrological cycle, and that was a big theme we discussed. Understanding large-scale climate dynamics and changes in circulation patterns, and then also changes in precipitation. And so we had 4 key scientific focus areas during our workshop. We talked about large-scale circulation and climate sensitivity. We had a focus session on air-sea interactions, which was more looking at modes of climate variability like ENSO, and seasonal to decadal prediction. Air-land connections, so here are our biology, climate feedbacks, evaporation, transpiration work that's been done, especially with remote sensing products of late. And then finally, our small-scale atmospheric processes, convection, clouds, precipitation. So just a quick highlight reel of some of the applications that, that have, again, been talked about at length at this workshop already. I'm kind of late to the party here. So there are critical new scientific opportunities that are afforded by remote sensing products. So in particular, the increasing availability of water isotope satellite retrievals from SCIMACI and ORA and NIASI and AIRS provide a point of comparison for validation of our isotope-enabled models. So these new remote sensing products have really provided some key constraints on Earth system processes and model physics. And we started off just with the total column water vapor measurements of delta D, but now that we have these satellites that sort of cut through the atmosphere with altitude, we actually have horizontally resolved water isotope measurements. So these have enabled, again, many meaningful comparisons and interesting science. So this is a figure from Adriana Bailey's recent papers showing the composite La Nina minus El Nino delta D at a fixed humidity. So it's normalized by atmospheric humidity on the left. And then on the right, this is ICAM5, same field, La Nina minus El Nino, over the period of time that test spans. So just a few years, maybe a decade or so, but even in that amount of time in the satellite retrievals, we can see sort of these big ENSO composite signals that allow us to check the fidelity of our simulations. I guess Jesse, Adriana, and I have done some work recently applying these satellite and water isotope-enabled model comparisons to better understanding large-scale circulation in the tropical Pacific. And so I actually gave a poster on this at our meeting in 2019, but most models show a slowdown of the Walker circulation, although it's accelerating in the 20th century and no one knows why, but we can use our isotope-enabled models to provide a prediction of, okay, if the Walker circulation slows down, what will that look like in water isotope space? So if you have a slowdown of the circulation, in the mid-troposphere, if we had a target, what would that look like in water isotopes? And so this is what we did, right? We can put some constraints on delta D in the mid-troposphere. And what we found is that essentially in a high CO2 environment or a warmer world, the gradient in delta D in the mid-troposphere sort of shallows. So in a control experiment in the modern, we have some difference in delta D from the Western Pacific to the Eastern Pacific. You warm up the atmosphere, Walker circulation slows down, and you kind of get this tilting of that gradient towards a shallower number. And indeed, if we look at those ENSO composites from tests in the tropical Pacific, it's, the satellite errors are large, but you can still see this tilting pattern towards sort of a reduced gradient across the tropical Pacific during El Nino events. And we also checked in some of the ISO-GSM nudged experiments to see if this relationship holds. And indeed, if we look at some of the bigger, warm El Nino events, we see a reduction in the delta D of vapor at around 600 hectopascals and an increase in the Eastern Pacific. So again, tilting that gradient closer together. So this west to east tropical Pacific delta D gradient can give us sort of a bellwether or an indication of changes in circulation. And we have to account for both thermodynamic and dynamic effects, but I think that there's powerful detection and attribution we could perform with using isotope-enabled models to get a prediction about how the climate system might change as we are, severely warming up the planet. And we can then go to the satellite products to check our understanding and to detect those signals. Another key area for development, I think, is using water isotopes for intermodel comparison, but also for refining model physics. And so this is a figure on the left here from Jun Hu, who is working in my lab for exactly 1 more month before he moves on to a faculty job. So this is just an example figure showing the change in the vertical advection of the delta D of vapor in SPATIAL, which again is a fast physics intermediate complexity climate model, against ICAM5, which is more of a Ferrari climate model. And so we used the water isotope fields to check the simulation of circulation changes in both models and used ICAM5 as a target, as the water isotope fields as a target for changing the model physics to improve the simulations. And one of the critical arguments that we make in this paper is that when we evaluate precipitation, winds, vertical wind, we get some comparisons that are meaningful. But when you look at the water isotope fields, you get more information, and it reveals hidden biases in the climate model that can guide improvements to the model performance. And so likely using the water isotope comparisons against our satellite observations, for example, provide a more stringent constraint on model physics. We've seen many talks, and Kay's summary talk yesterday was a fabulous sort of introduction to this point, right? There have been rapid gains in water isotope-enabled models in the data assimilation framework. So going back to some of the earlier work about 10 years ago, 5 years ago, using observation system simulation experiments with water vapor information. There's been a number of papers and also many of the talks and posters at this workshop expanding this into using more models and creating new reanalysis products. And we had a great discussion yesterday about the ways in which water isotope fields can actually improve the skill of our reconstructions. And this is now the gold standard in the paleoclimate world as well. So this is a figure from the last millennium reanalysis, which is a paleoclimate data assimilation product, just showing sort of the data assimilation framework. So we have our climate model prior here on the left, and then we have some conversion between our paleoclimate observations. So in the in the weather forecasting world, we're using much higher resolution measurements of water vapor isotopes. In the paleo world, we're using annually resolved paleoclimate measurements and assimilating those into the climate model using offline data assimilation. The key here is that this conversion between the climate state and the paleoclimate observation really depends on having water isotope physics available in the climate model. Because if we're going, and I'll talk about this more later, from temperature, precipitation, wind to oxygen isotopes in coral, right? Those things are not in the same unit. And so we need that water isotope enabled field. We need those fields to be able to connect the proxy observations into the data assimilation. I wanted to highlight the newest, as of I think 2 days ago, data assimilation product that's come out in the world of paleoclimate. This is Matt Osman and Jess Tierney's reconstruction of the last glacial maximum to present. All of this data is now online. It's a really incredible data assimilation product. And again, this was dependent on the ICESM prior to capture the full range of variability back in time. As was mentioned earlier, water tagging experiments and identifying moisture source and trajectory is also a really key area that we could expand in. These are some figures from Jesse Nussbaumer and David Noon's paper looking at atmospheric rivers in the Western United States. So the ability to, isotopically tag regions of the tropical Pacific or other areas of the world. And, in the bottom panel here, figure out the fraction of moisture and its isotopic content being delivered to a certain region in the United States as a really powerful tool that I think could be more widely applied, especially in paleoclimate studies where we're not sure, is the moisture coming in from the Gulf of Mexico or, the tropical Pacific? This is a key tool we could use to better constrain that. In my attempt to provide a broad overview, I did a deep dive on moisture tagging and found the following, once again, paper from 1986. We must respect the work that comes before us. But I think this is maybe, hopefully, let me know if I'm wrong, the first water tagging paper using the GISS model that I could find. And their tagging regions are a little bit different from the ones we're using with CAM, but still very exciting that this work was, again, we see Jean Giselle really pushing the envelope here back in the 80s. Tomorrow, or today, not tomorrow, it feels like tomorrow since it's still 4 o'clock in the morning, there will be a poster on a similar water tagging experiment where we were focused on the contributions of moisture to Antarctic ice core sites. So again, in the paleoclimate realm, if we're interested in where is this isotopic moisture being sourced from, we can use these water tagging experiments to get a better handle on, is the moisture coming from the Southern Ocean or the subtropics? And so there's a poster later today by June and Yuzhen Yan looking at impacts of sublimation and also using these moisture tagging experiments. Okay, we've seen many, many talks, and this is far outside my wheelhouse, on the understanding of mixing and cloud processes. And I think this is really a key area of growth where our field can use the tool that is water isotopes to really advance our understanding of, from everything from what David talked about yesterday, cloud microphysical processes, but also, looking at sort of large scale cloud cover. So June Hu gave a talk yesterday on the relationship between shallow convective mixing and low cloud cover. And I think coming back to the satellite retrievals, there are certain fields that are very, very difficult for us to observe in situ or via aircraft measurement or via satellite retrieval, but water isotopes are observable. And so we can fill some key gaps. In this case, looking at delta D profiles in the vertical to elucidate our understanding of shallow convective mixing and how those fields affect low cloud cover. So we can compare how those relationships operate in our GCMs to how they operate in the satellite data products. So hopefully a paper on that topic will be coming out within the next couple of months or so. I saw some excellent work yesterday, really exciting, on tropical cyclones. So here in Houston, we are no stranger to big hurricanes. And I've only been at Rice now for 3 years, but I was chatting with some of you yesterday about setting up a precipitation collector on the roof here because, we get hurricanes every couple months effectively here in hurricane season. This is Hurricane Delta, which just narrowly missed us last year. And if we had, I see that the community is moving towards isotope-enabled modeling of these big tropical cyclone events, but we don't have the observations. We really need to critically fill the observational gap in order to move this forward. All right, so I'm almost done. I just wanted to quickly go through the last part of my talk, which is a call for a new stable water intercomparison group, or SWING 3. And so we know that our colleagues who work on CMIP and PMIP, the Paleoclimate Model Intercomparison projects, are providing these common ground experiments with the same boundary conditions to look at intermodal differences to the same external forcing, but these MIP efforts are not including water isotope fields. And so despite all of our efforts to provide the hierarchy of water isotope enabled models and tracers, we haven't done a swing effort or a stable water intercomparison group since 2012. And the last papers on this topic were mostly written by Camille, again, about 10 years ago. And so swing is ready for round 3. Let's do it. So we talked about this yesterday in our discussion group T1, stable water isotope observation model intercomparisons. And I think today we can really decide, what are the key experiments we want to run? Do we want to include LES? There are a lot of different questions we need to talk through. We could have parallel efforts doing cloud resolving LES model comparisons and GCM comparisons. So we really need to convene internationally to perform the next round of isotope enabled model comparisons. So it'd be great if we could take some time today in our working group to solicit feedback and set a formal set of scientific goals. I'll also say that this is work that I would hope could be funded. And so maybe some discussions on funding opportunities across continents would be helpful as well. Our charge is really to reduce uncertainties in our climate model simulations. And so I think we should focus our discussions on how can providing these intermodal comparisons and what fields should we be saving to really help the community improve or reduce uncertainties in climate model experiments. We know that there are large uncertainties caused by how will humans behave, but there are also uncertainties, structural uncertainties in our parameterizations of cloud microphysics, et cetera, that we could help with in our community. Okay, so I think we need to ask ourselves, how explicitly can we improve GCMs with our water isotope comparison? And as I mentioned earlier, water isotopes expose model uncertainties that other fields do not. And then in the same way that they add information for data assimilation, they can also help improve model physics. Okay, as I mentioned, we also probably want to talk about which boundary conditions do we want to test. So obviously a 20th century run will be crucial, but we can also refine our models with out of sample targets from the past. So focusing on key periods like the mid-Holocene or the last glacial maximum when climate was really vastly different from today, and we can test our model physics on a very cold climate, for example. So we're going to need to do some strategic planning in coordination with the observational community to see, okay, what validation products do we realistically have right now? And to that end, I think we really need to formalize a buddy system whereby collaborations between paleoclimate data generators, but also modern observationalists and paleoclimate and water isotope enabled modelers can come together, right? We can run these model simulations till we're blue in the face, but what we really need is observations and especially potentially water vapor isotope measurements in the present. And so we talked a bit yesterday in our session about using DXS as a target for just basic improvement for kinetic fractionation over the ocean. And then there's some final additional needs. I know I have 1 minute left. We have some final additional needs and missing quantities. So we have isotope ratios in soil water. Some models have them, some don't. Again, we're fundamentally limited by observations. So lobby your program managers. We really need more modern observations. And then finally, I think that lack of observations really limits our data assimilation efforts. So there's some big pushes on both the modeling and observational sides needed. Okay, and then finally, I'd just like to end by noting the critical connections to the past. So I mentioned earlier, we have climate models, we have paleoclimate observations. There's a huge language barrier that exists between these types of information. So, we can create an inverse model where we predict temperature as a function of our proxy measurements. And then we can also do forward modeling, whereby we predict a proxy value from our climate model variables. But this requires us to have isotope tracers in our models. So water isotopes are really a common unit or a lingua franca that link paleoclimate observations to models. And so paleoclimate data, or paleoclimate, excuse me, water isotope-enabled models are a critical link for our proxy system modeling efforts that are ongoing. And we can think about this as a formal data model comparison schematic, right? We have our climate models, we have our proxy system models, we have our observations. Now we're incorporating data assimilation. And this critical component provided by the water isotopes allows us to compare apples to apples, even if they're computer apples to computer apples, but we can do better in terms of making more robust comparisons across the board by incorporating water isotope fields into our models. So thank you. Excuse me?
Please think about concluding. Thank you.
Yes. Okay, I'm all done. So anyway, I just wanted to end by saying this is a very special community. It's really inclusive and very tilted towards early career scientists. I'm very grateful to be a part of the community, and thanks again for the invitation to speak. Thank you very much. And just to, as a last plug, I'm trying to hire a postdoc in water isotope modeling. So if you're looking for a postdoc, please reach out. Thanks very much.